quantum teleportation comparison. So that's what I want to do today, to explore a bit farther, sort of, the continuous versus the discrete quantum computing implementation. So what Xanadu does, and I am still not sure whether I pronounced that correctly, but as nobody has complained so far, I think that's the correct way of pronouncing it. And then the sort of the discrete version of quantum, because so this is the IBM experience and this is Xanadu. I'm going to try, here I found the quantum teleportation. Here I probably need to find it. I think it was in Strawberry Fields documentation. There's an algorithm somewhere. Let me see. Blah, 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 blah. Variational circuits, quantum nodes, introduction. Maybe I should just search teleportation. Docs. It's not, that's not, no, but it's, that's not Strawberry Fields, Penny Lane. I'm stupid. So, software. Strawberry Fields. Okay, now this is Strawberry Fields. Strawberry Fields, yeah, exactly the right one. Yeah. Cool stuff, by the way, here with this. Simulating it as a continuous variable. So, I haven't tried the editor yet. I might probably play with this as well. So, teleportation. I just keep I'm getting distracted. Teleportation. Yeah. Quantum teleportation tutorial. But is this or is this? Because here we solution laws and direct convention from quantum algorithms. Quantum algorithms. State teleportation. I think that's what we want to do. What else was there? State, gate. This is something that I'm guessing the equivalent in discrete quantum computing would be sort of the matrix teleportation. So sort of you encoding something in the gate. I don't know, encoding a matrix in a gate and then having the same effect on the other one, maybe something like that. Gaussian cloning, boson sampling. Quantum neural network. This is something that I also worked on, and that I also have done a discrete quantum computing version of it. And okay, but let's take a look at that, and then next we'll take a look at beam splitting, and then probably we'll just go back to the actual yellow Submarine project, because I think I'm diverging too much of that, and then probably I'll try to understand that based on what I understand here. And then I might make a separate series really to dive into Strawberry Fields or Xanadu, because it's just going to be, I think I'm losing the focus here a little bit. But let's just get onto it. So state teleportation. I took a look at this briefly in the other video as well. So because beam splitting is the way you create entanglement in continuous quantum computing. But let's refresh our mind, my mind actually, not yours. So what was the teleportation here kind of thing, right? So Alice and Bob create an entangled bell. They hold one of the qubits, each of them. I think exactly. By using Hadamard gate, and then apply a SIMD gate. Okay, so they create a bell state basically, and then they have each of them one qubit. Alice applies a control node gate to Q1, controlled by this. Next, Alice applies a Hadamard gate and applies a measurement to both qubits that she owns. Then it's time to for a phone to call Bob, she tells Bob the outcome of her 2-qubit measurement. Depending on what she says, Bob applies like a different gate. And exactly, how will the test result in a real quantum computer? Blah 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 blah. Here we had the circuit. So this is the Q. This. See if I can zoom in this a little bit. Oh, it seems I can. Maybe I can open the image in a new tab. That makes more sense. Yay. So this basically the basic idea here. So you've got an entangled pair of qubits. Exactly. You've got an entangled pair of qubits, and so Alice does this on her ancilla qubit, which basically I'll just try to open up a circuit so we can take a look at it. I just don't want to repeat the whole thing again, but actually I realized that I kind of forgot a little bit about it. So, but it's been a while since me using the actual. So it's 3. So Alice does this and this, which basically gives her a superposition. Alice owns Q. To keep it transfer one of them to the bell. Harman get and apply signal get until keep it controlled by the one bells. So I don't know why the Z is here applied. Okay, but the idea here is you apply a Hadamard here, and then you do a control. So Alice entangles her control qubit, her ancilla qubit with her own qubit, in a way that they are, let me see, correlated, right? So if I now do this, they're always going to agree 0, 0 or 1, 1, these two here. So, and then she goes ahead and she does this operation. Just let me just I'm a bit confused by the Z here right now. I think it's not needed. So then she applies a measurement here. That's not what I'm looking for. That's what I'm looking for. A measurement to both qubits. Okay, so I mean, of course, these two qubits have been entangled before, so there's also these and these entanglement. And now Alice basically applies a Hadamard here. Why was this Hadamard needed? she applies a Hadamard. Because then, it's funny because it's like it's one of the first things I did, and I kind of realized it's hard to come back to those things. It's pretty hard to come back to those things, and it's pretty hard to read the circuits like that. I remember that I did this like really with the zeros and ones on a notepad, and it worked fairly well. But I thought by now I'd be able to actually. It's time for Alice applies Hadamard gate and applies the measurement to both qubits, and she owns. So if she measures 0, then Bob shouldn't do anything. If she measures 0, 1, 1, 0, 1, 1, then Bob should apply the X gate, the Z gate, or the Z and the X gate. So basically, I'm jumping a lot. Yeah, okay, but that kind of works. So that kind of works with. So basically, because these measurements, these partial measurements, what they're doing is they're kind of collapsing the rest of the state, right? So if she had a I don't want to use the notepad because I know because that's not scalable, and I just know that it's going to be easy to understand like that. But I try to understand that just by reading the circuit, kind of. But I feel I'm missing that intuition again. That sucks. So this is entangled exactly, and this is entangled, and then so when we measure these, and we measure that, basically, this is what's going to make the difference, right? So if you measure 0, 0, if you measure 0, 0, it means that was a 0. It means that never happened, that control node. So it means that was a 0. So it means that also never. So it's kind of like feels awkward, but it's like, so let's do the case 0, 0, right? So by meaning that this is the 0 and this is the 0. So if those measure 0, it means that this was 0, right? It means that this control node never happened, which in turn here means that this was also. No, I cannot say that this was 0, right? Because this was 0 and then it was in a Hadamard. So this was still 0 and 1. Yeah, okay, but this was still 0 and 1. This was still 0 and 1, right? Exactly. So this means that because this could be 0, 1, and if it's 0, then Bob's qubit stays 0, and if it's 1, Bob's qubit stays 1. We've effectively, kind of teleported this, right? So this means that Bob needs to do nothing and just measure. That's what they're saying here. Exactly. So Bob does nothing, just reads the qubit and that's it. So exactly. So you see how this is, it feels like you got to go down to the measurement and then kind of go back and see and understand why this works. That kind of, it's one way to read the circuits, but it's not trivial. Bit of coffee. So if it's 0, 1, right, then it says apply the X gate. So then if it's 0, 1, it means we've measured a 1 here. Which in turn means that I'm not so sure if this is correct, right? But it means that this was a 1, which means that the sign here was flipped. Here, the sign was flipped. The sign, the amplitude. So the control knot was applied. And if the control knot was applied, and we measured a 0, it means it was a 1 here. It means that because this was 1, the control here, this control knot was applied. But because exactly, this control knot was applied. So basically, this qubit was then kind of moved to 1. So I think that's what's happening here. And then, which then means that in this case, because this is a concrete example, right, where this is a 0, in this case, then we got to apply a next gate to turn that into, into its original thing, into the 0. So the concept here is that the idea of the discrete, and I'm probably missing some stuff, so I definitely should do a sort of a refresh on this. Man, there's so much to explore. It's just it's a lot of fun. But this basically means the concept here is you have you use partial measurements. So Alice entangles an ancilla qubit with her own to then measure, like she does the Hadamard operations and whatnot, and then she measures and then backtracks that. So because of the measurement that she's done, then Bob knows what transformations he has to make in order to get Alice's original state. And I'm guessing this is just one implementation. So, but this is the basic idea. Whereas here, in Xanadu, it's a sort of a similar concept, because you've got conditional actions based on measurements, right? So what they say is, while originally designed for discrete variable, blah, 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 okay, the results showing in the following circuit. So the thing is, I don't know why they use the X and the Z gate, which are not, are they? I don't think they are continuous quantum computing variables, operations. So, but it's the same concept, right? So you see here that you've got the ancilla bead. Is this the ancilla one? I think so. Because what you're teleporting is the momentum and the position. So and so you're entangling, Alice is entangling that and then making a measurement. And then based on the measurement, so a measurement, and here the thing is, because you have different types of measurement, if I remember well. So you've got measurements on position, measurements on momentum, and some other fancy measurements like counting stuff, because this is really tied to the implementation, right? Which is the photonic type of implementation. So this is not like, I think the measurements here really do not map to the measurements in discrete quantum computing, but it's more like, okay, how do we measure our beam of light, right? How to measure the photons? Like we can count them, we can check their momentum, stuff like that. I think so. Basically, that's the idea, um, because. But I'm curious about what is the entanglement really looking like inside, because the beam is the same concept that then the phase and the moment that the momentum and the position are always agreeing, for example. Is this what the beam splitting does? Maybe that's what I should take a look at now quickly. But that's the concept is roughly the same. So you measure position and measure momentum, and then if you measure position, then you go sort of I assume the x is displacement, and I don't know what the z is. If it's the same thing here. So cumulus are spatially separated. Teleport her known state to Bob. Alice now performs a projective measurement of her entire system. No, this is the one that she wants to teleport. This is the Ancilla one, I think. No. No. It's different. It's a little bit different. There's no Ancilla qubit here, a Q mode. Is there? I don't think so. There are three because one is used for position and another one for momentum, one for position, right? Cumulus are now specially separated. Teleport her known state. Alice now performs a projective measurement. So the first one is the actual Q mode to teleport, the state to teleport. Projective measurement of our entire system into the maximum entangled basis states. This is done by entangling this and this via 50-50 beam splitter. Homodine measurement in the X and the P quadratures, respectively. The results of these measurements are then transmitted to Bob, who performs both a position displacement, exactly, and a momentum displacement, okay, conditional to the P measurement. Yeah, but to recover the exactly transmitted state. But those displacements should be parametrized, if I understood well the whole concept here. So how does Bob know the parameters for those displacements? I don't know. This can be easily implemented using the Blackbird quantum circuit language. Ooh, Blackbird. Sounds cool. Okay, that's it. Let's take a look at beam splitting to understand a bit more the anatomy of this entanglement. Beam splitting. Beam splitter. Okay, no, I won gates. Quantum programs. I want gates. Introduction. States gates. Do we have here BS? Yeah, beam splitter. Here you have beam splitter. So what is it doing? What is it doing? I have no idea, absolutely. What does this here mean? Homodine measurement, heterodyne measurement, photon counting. Yeah. So you see the homodine measurement measures the position. The heterodyne measurement measures position and momentum. Then photon counting. Okay, whatever. But what is the beam splitter doing? Beam splitter. Beam splitter entanglement. Beam splitter entanglement. Yeah, that's a paper. Which Quora physics forums? Just the dispute conditions for two photons to be entangled by a beam splitter. Lots of references given by the forum users and conclusions. Must entangled pairs. Must they already be part of the entangled pairs, and does the beam splitter just swap the entanglement between the members? Can the beam splitter be used alone to entangle photons, or can it entangle them only in the presence of many other elements like polarizers, wave plates, prisms? And entanglement. I mean, I don't want to go so much into details. I just want to know what's the entanglement that this creates. Like, beam splitter. Beam splitter. Gates. Because it also has parameters. Apply the beam splitter operation to the specified Q modes. It is assumed that these real parameters. Transmitted amplitude, reflected amplitude, first mode, second mode. What is a transmitted amplitude? And glossary. References in further reading. Glossary. Beam splitter. Nope. Okay, here we've got some definition. For the annihilation and creation operators of two modes denoted, the beam splitter is defined by. Okay. They will transform the operators according to. Therefore, the beam splitter transforms two input coherent states to two output coherent states, where by substituting in the definition of the creation and annihilation operators in terms of the position and momentum operators, it is possible to derive an expression for how the beam splitter transforms the quadrature operators. Okay, so it seems like it is correlating. It seems like it's correlating the position of one with the position and the momentum of the other. I'm just guessing, right? It's just kind of correlating these with these and these. Okay. Action on the position and momentum eigenstates. Okay. Controlled phase, cubic phase. This is some pretty dense stuff. But it seems like the beam splitter is correlating position and momentum. So the position of the one Q mode with the position and the momentum of the other one, and the momentum of the one Q mode with the momentum and the position. There's sort of like a difference here with the sign is up here, the minus sign is up here, and here is up here. Whatever that means, really. So it's kind of, where am I? I wanted to go to the circuits, quantum algorithms, state teleportation. But as I was saying, So it correlates those things. And then it would make sense that you measure the position and the momentum, and then you can probably derive what are the parameters for the displacement you must do here. Correct? I don't know. So let's see what's happening here. So let's take a look at the code a little bit, if I understand, if it can be understood. PCI, Alice, and Alice is 1, Bob is 2. So there's a beam splitter. There's a beam splitter, and then there's squeezed. Why was squeezing? I don't know. Squeezing. Then beam splitter, Alice, Bob. Alice performs the joint measurement. X gate scale PSI. Some important notes. Infinite squeeze vacuum states are not physically realizable. The function scale, whatever that means, the function scale can be imported from this. The BS gate accepts 2 arguments, theta and phi. A variable storing the value of pi is used for setting these parameters. In Python, this can be imported from NumPy. What is psi? So you do, so here the X gate, because it seems like it's not a conditional application, it means it's applied yes or yes, right? It's applied yes or yes, it's just somehow parameterized. So that's kind of the difference here, because we're probably dealing with, because of the continuum thing, I guess. I mean, intuitively, that seems to be what's going on. Z gate, Alice. But measure X, measure P. Okay. So you measure X into psi, and you measure P into Alice. Okay. Okay. So you see. Okay. So then those values. So I was confused by the variables. And there's some sort of scaling going on, which I don't know why, but the idea is you use the exact results of your measurements as input for the X gates and the Z gates, which the X gate and Z gate, which is then, I guess, like parameterizing the displacements. It's parameterizing the displacements. Okay. So this is really at an intuitive level fairly more simple to understand, because it's kind of, it feels more logic. It's like you entangle this with your channel or whatever, right? If you want to call it this way, or you entangle this with another qubit, so the positions, and it seems like really what it's doing is just it really entangles them in the sense that they get the same position and the same momentum. I mean, there's a scaling factor here, but it's what this seems to say. It's pretty fairly simple. It is here. Or it seems the code seems pretty fairly straightforward. So, and then literally the measurement, and then literally you've also entangled that with this one. So you kind of you entangle the 3 of them really. And it's just, you need the 3 of them because you need to destroy those, because you measure them, right? So you need to destroy this one in the middle. And then you literally apply whatever you measure position-wise and whatever you measure momentum-wise as displacements to Bob's Q mode, and then you have it. It's funny because it's much more complex from a theoretical perspective, like what those things are kind of looking like, but at the intuition level, it seems more obvious. At least to me, that seems fairly obvious and fairly similar to what you would usually do with a traditional classical computing thing. You would basically kind of copy stuff and then, and basically use the result of your operation as a parameter of another operation, etc. So this feels quite quite intuitive. Whereas the discrete one, and I might be missing. Don't get me wrong. Don't get me wrong. I might be missing here some of the details. So this might be BS, not as in beam splitting, but as in the other meaning of BS. And whereas here is complicated because you gotta backtrack from measurements. You don't understand the circuit because of the entanglements. I think the entanglement here is fairly complex because of the controlled operations. Intuitively, it's just a bit more mind-bending, I think. This is just a bit more complicated, but you can grasp it easily, I think. Okay, cool. I hope that was helpful. I'll try in my next video to really go back to the yellow submarine project and then actually try to dig into that a little bit more. And then kind of jump back and forth the strawberry fields documentation and the code, and then see if we can grasp that. It might be too early, but let's give it a try. Cool.